For decades, we've been told the same story about Jupiter. It's the gentle giant of our solar system. Earth's cosmic bodyguard. A planet so massive that it protects us by pulling dangerous comets and asteroids away from the inner solar system before they can reach Earth. It's one of the most repeated facts in space documentaries. The problem is, it isn't actually true. Research led by planetary scientist Kevin Grazier suggests that Jupiter doesn't simply protect Earth. In many cases, it does the exact opposite. Instead of acting like a giant shield, its enormous gravity can redirect debris from the outer solar system and send it toward the inner planets. Grazier himself described Jupiter as acting more like a sniper than a shield. That single discovery completely changes the way we think about Jupiter. Because if we've misunderstood its role in our own solar system, what else have we gotten wrong? As it turns out, quite a lot. The deeper scientists looked, the stranger Jupiter became. Storms that can tower more than 60 miles into the atmosphere. Lightning that forms in ways we once thought were impossible. Giant hailstones made from ammonia and water ice. And buried deep beneath those clouds is a mysterious interior that may have been permanently reshaped by an ancient collision billions of years ago. I'm going to save that discovery for the end, because once you understand what's hiding at Jupiter's center, everything else about this planet starts to make a lot more sense. Let's start with the shield myth, because it matters more than it seems. Kevin Grazier, formerly of NASA, has spent years debunking the Jupiter shield idea. He published a paper titled Jupiter as a Sniper Rather Than a Shield, and with each successive study, he increasingly demonstrated the ways in which Jupiter is actually a pernicious, indirect threat. Using a model of around 40,000 planetesimals, Grazier and his colleagues found that debris in the outer solar system initially had circular orbits and posed no threat to Earth or the other inner planets. But through a series of close gravitational encounters with the outer planets, especially Jupiter, those objects assumed more elongated orbits and were handed down toward the inner solar system. Grazier's own comment on the shield theory, I would say that it has been laid to rest. Our simulations show that Jupiter is just as likely to send comets at Earth as deflect them away, and we've seen that in the real solar system. So the planet that every documentary presents as Earth's protector is, by the scientist who studied it most closely, essentially a wash at best and a threat at worst. That reframing matters because it sets up everything else. Jupiter isn't a calm presence in the outer solar system. It's an active force, reshaping orbits, redirecting debris, and running one of the most chaotic atmospheres in the known solar system. And that atmosphere is where things get genuinely hard to believe. Most channels, when they talk about Jupiter's storms, just say, they're big and move on. But the reason Jupiter's storms are so extreme is actually a physics problem, and it's one that almost nobody explains. Convection operates differently on Earth and Jupiter because Jupiter has a hydrogen-dominated atmosphere, which means moist air is actually heavier and harder to bring upward. On Earth, water vapor is lighter than the surrounding nitrogen-heavy air, so storm clouds rise relatively easily. On Jupiter, the moist air is the dense stuff, it has to fight its way up against the atmosphere pressing down on it. So storms on Jupiter need an enormous amount of energy just to get started. And when they finally do rise, they release all of that stored energy at once, higher in the atmosphere, more violently than anything our planet can produce. The result of that physics is what UC Berkeley astronomer Michael Wong has been tracking with NASA's Juno spacecraft. The powerful lightning generated by Jupiter's storms is likely produced by massive, towering storm systems that can reach over 60 miles high. For comparison, the tallest thunderheads on Earth reach about 12 miles. These storms don't just sit at the surface level of the atmosphere either, they penetrate deep, and they carry something Earth storms don't. Juno made 12 passes over isolated storms, and was close enough on 4 of them to measure microwave static from lightning. The flashes averaged 3 per second during those passes. Of a total of 613 pulses measured, the power ranged from roughly that of a lightning bolt on Earth all the way up to 100 or more times that energy. That study, led by Michael Wong at UC Berkeley, was published in AGU Advances on March 20, 2026. Now here's the part that makes Jupiter's lightning even stranger, and this is the open question that scientists still haven't fully answered. On Earth, lightning requires water clouds. That's the basic rule. But Juno found that at least one type of Jovian lightning forms high up in Jupiter's atmosphere, where it's far too cold for liquid water to exist. Instead, this shallow lightning appears to be caused by ice crystals and ammonia colliding, a form of electrical discharge that has no real equivalent on Earth. The planet is producing lightning through a mechanism we didn't even know was possible until we got there. And while we're in the atmosphere, let's talk about what falls out of those storms, because this is the detail that tends to stop people cold. Jupiter has correspondingly enormous storms, some of which last for centuries. Juno found that lightning storms on Jupiter, which on Earth are more common near the equator, are instead concentrated at the poles, and those polar storms drop softball-sized hailstones made of a mixture of ammonia and water ice. NASA scientists nicknamed this phenomenon mushballs. The storms are so energetic, and the chemistry so unusual, that they produce a type of hail that doesn't exist anywhere else we've observed. And if you go to Jupiter's poles and look down from above, you'll see something that still puzzles scientists about how it stays stable. Chains of continent-sized cyclones sit locked in geometric rings at both the north and south poles, powerful, Earth-sized swirling storms densely packed together, rubbing against each other, some reaching 30 miles in height and hundreds of miles across. They don't drift. They don't collapse into each other. They just hold their positions, indefinitely, in a configuration that shouldn't be geometrically stable by any simple model we have. So we have storms that work backwards compared to Earth's, lightning that breaks the rules for how lightning is supposed to form, hailstones made of ammonia, and cyclone formations that shouldn't stay locked in place. All of that is happening right now, continuously, and has been for longer than human civilization has existed. But the thing I promised to save for the end, the one that changes how you see all of this, is what's at Jupiter's center. For a long time, the assumption was that Jupiter had a compact, solid core. Dense material packed at the center, surrounded by layers of gas and liquid. That's the intuitive model. Michael Wong, the same planetary scientist who led the lightning study at UC Berkeley's Space Sciences Laboratory, has been part of a broader Juno-era effort to understand what's actually down there, and what Juno's gravity data revealed is that Jupiter's core isn't compact at all. It's a bloated, diffuse region stretching nearly half of Jupiter's total diameter. Scientists refer to it as a fuzzy core. The leading hypothesis for why it looks like this is that Jupiter may have been struck by a massive object early in its history, an ancient giant impact that mixed its dense central material with the surrounding gas layers, and the planet never fully separated them back out again. The core we see today might be scar tissue from a collision that happened billions of years ago. That's not a settled fact. It's a hypothesis built from gravity measurements, and it's still being worked out in real time. Which brings us to the bigger point here: Jupiter's violence isn't just a historical story. Studying storms on Jupiter sheds light on storms on our own planet, which are still not completely understood. As Wong noted, scientists over the last decade have discovered several new types of electrical phenomena associated with thunderstorms even on Earth. We are still learning the basics. And Jupiter, which has been throwing lightning bolts since before the dinosaurs, had its lightning confirmed for the first time only in 1979, when Voyager 1 picked up radio signals consistent with electrical storms, but in a completely different radio range than lightning on Earth. Nearly 50 years after that first detection, the exact mechanism behind the most powerful lightning in the solar system is still being pieced together. That's what makes Jupiter genuinely different from every other planet. Saturn has storms. Mars has dust. Venus has acid clouds. But Jupiter is the one place where the violence is so extreme, so layered, and so physically strange that we keep sending spacecraft there and keep coming back with surprises. A fuzzy core that might be an ancient impact scar. Lightning that doesn't follow the rules we know. Cyclones that hold geometric formations they shouldn't be able to maintain. And a gravitational influence that, rather than protecting us, is just as likely to redirect danger toward us as away. If you've been thinking about Jupiter as the quiet, heavy presence at the edge of the solar system, the planet that just sits there keeping things in order, the reality is something much harder to categorize. It's the most active, most violent, and in many ways least understood planet we have access to. And the more closely we look, the more unsolved it becomes. If this changed how you think about Jupiter, drop a comment below. I genuinely want to know which part surprised you most, because this one had a few moments that stopped me while I was putting it together.